Hello students, we're going to review the pH of salts. And we're going to start off with some neutral salts. And to recognize neutral salts, they're going to have two components. They're going to have group 1A or 2A cations together in an ionic compound with the conjugate base of strong acids. So let's go ahead and identify those two ideas. So Na plus, K plus, Li plus, Ca2 plus. Okay, so you're getting the point on that, hopefully, right? Group 1A or 2A cations. And then the conjugate base of strong acids, and the strong acids that we're talking about will be monoprotic. So, for example, the conjugate base of hydrochloric acid, chloride, bromide, iodide, nitrate, perchlorate, and the borderline chlorate. So what I think is really important to realize is that any combination of these guys will give us a neutral salt. And why is this the case? Is because, and I'll take the chloride here as an example, there is no reaction to any great extent of chloride plus water as a base. They are extremely weak bases. And so there is no reaction there. Okay, so if I see, let's say, calcium nitrate, what you have to think of is that you're really talking about identifying calcium, right? Breaking it apart. Identifying them as a group 1A cation with a conjugate base of a strong acid, right? There's our friend nitrate on the list, pH 7. And it won't matter what concentration of that salt it is. pH of basic salts. So we're still going to have our cations from group 1A and 2A. Lithium ion, sodium ion, potassium. With our anions going to be the conjugate base of weak acid. Now remember, there's too many weak acids to list. So I'll just do a little sidebar here of just some common ones like acetic acid, hydrofluoric acid, bicarbonate ion is a weak acid. If you're not sure what I mean by that, you're going to need to go and look over again the PowerPoint on polyprotic acids. So these are just some good examples. So their conjugate bases of these weak acids would be acetate, fluoride, carbonate. So for example, if I see sodium acetate as my salt, then I know that its pH is going to be greater than 7 because it is sodium ion with acetate. If I have sodium ion with carbonate, pH greater than 7 as well, because it has sodium ion with carbonate. So pairing a group 1A and 2A cation with an anion of a weak acid, then you know that their pH is greater than 7. So let's go ahead and do a calculation with that. We want to know the pH of a 0.10 molar sodium acetate. Okay, so what is the pH? We would split this apart. Sodium ion does not react with water. Acetate is a base. Now, once we know that, we also know it's a weak base, okay? And so this becomes kind of the easier part. It's just really this first part that's identifying what it is that's harder. So I would just treat acetate as a base. What do bases do? They accept H+, Bronsted-Lowry. And they make hydroxide. Now, I know as a student, this is going to look confusing because you do have a weak acid here. But you have a strong base. Who's going to win this war is the hydroxide. It's a strong base. It's going to essentially crush that weak acid's ionization. So now I'm going to set up my ice chart. And then I'm writing this out as a base, correct? So we really need Kb. Now, if you look in the back of your textbook or you look on Google, whatever, it's going to be hard to find. So instead, what we have to do is understand that in the back of the book is the Ka of acetic acid. So the Ka of acetic acid is 1.8 times 10 to the negative 5. So to find Kb, Ka times Kb equals Kw. And remember Kw, 1.0 times 10 to the negative 14. So if I divide this Kw by that Ka, I'm going to end up with 5.6 times 10 to the negative 10. Okay, so Kb equals Kw divided by Ka. Now that is super small. So small that for sure we're going to ignore x on that bottom. And then the calculations definitely simplifies. So you're going to take the 5.6 times 10 to the negative 10 times 0.1. And then we're going to take the square root of that. And I'm going to get 7.5 times 10 to the negative 6 molar. That's the hydroxide ion concentration, because this is basic. Then we'll find POH. And this is where things you really need to kind of speed stuff up and understand that we're just taking the negative log of that number. I get 5.13. Oh, I actually get 5.12 if I use this rounded value. And then to get to pH, we subtract that number from 14. Right? We'll take 14 minus that number. So just treat these ions as weak base And then it's the same calculation as if you were doing, let's say, 0.1 molar of ammonia. They're all weak bases. Let's look at the pH of acidic salts. So the pH of acidic salts. Acidic salts, the way we're going to recognize them is that they're going to have the conjugate acids of weak bases. So our weak base will be, let's start off with our friend ammonia. NH3. Its conjugate acid is NH4 plus. So these guys here are going to be these acidic salts. In the family of ammonia is CH3, NH2, CH3, 2NH. Now this will be perhaps the third time we've gone through this. So make sure that you are reading and you're starting to memorize some stuff, right? So this is that family of ammonia that these guys all have the lone pair that's implied. And then their conjugate acids. Whoops, I didn't need the brackets there. So, okay, that's plus. These will all act like weak acids. And then who's going to be in there as a salt form? Well, the ones we're going to be looking at, they're going to be paired up with the conjugate base of strong acids. So it's going to be NH4Cl, NH4NO3. Could even get really fancy if we wanted and do like CH3, 2NH2NO3. See, these get very complicated kind of quick. These ones then will have the anion from strong acids. And so essentially what we're looking at there is that this part that I've underlined is neutral, whereas the ammonium ion part is acidic. Okay, so let's look at a pH calculation. We have the pH of 0.1 molar ammonium chloride. We'll split it up into NH4 plus, Cl minus, chloride neutral, conjugate base of a strong acid, NH4 plus acidic. We'll write